we saw the general solutions. We don't have to do this many times. We did it once and for all. It was an integrating factor. It was the general solution, and we looked at a specific case where A and B were both non-functions of time. And again, we allowed time to not necessarily start at 0, it could start at any time, say t1. And we solved a number of problems that generated linear first order differential equations. But what we noted was in real life, linear problems are not the rule, they're sort of the exception. Most problems tend to be nonlinear. So the question is, what do we do when we have a nonlinear problem? When we don't have general methods for nonlinear problems? Sometimes we can get lucky that we can solve them exactly. Sometimes we can solve them numerically, and we'll discuss that as well. But the first line of defense is to do linearization. And as we saw last time, what linearization means is that we approximate a curve by the tangent to the curve. And we rely on Taylor's theorem, which you had in your freshman calculus class. And if you took calculus earlier, you would have had it there, which says, and here I wrote it a little bit more carefully. Here I could be in any dimensional space I like, but if f of z is n times differentiable in some region, and the region generally is, if I'm in two-dimensional space, you can think of a circle with the center of z at z0. So if it's n times differentiable anywhere in the circle. If I'm in one dimension, then it's in an interval whose center is z0, and the width of the interval is r. So we want it to be n times differentiable in that interval, or in that circle, or in 3 or higher dimensions in sphere. And then what Taylor's theorem says is we can always write f n plus 1 times. We can always write f at any point in that circle. So here I have a circle, here's z0, here's r. I can go to any point on the circle z if I'm in 2 dimensions. If I'm in 1 dimension, then here is z0, and this distance is r, and I can go to any point in that interval. This is 1 dimension, this is 2 dimensions. And I can write f at any point in this circle or in the interval as f at the center plus the derivative, first derivative over 1 factorial times the distance, plus higher order terms, the second derivative over 2 factorial times z minus 0 squared, as many derivatives as I have differentiability, and then I even can estimate the error. Now, we're not going to go into this in this class, but we also have an estimate for the error. So we know that the error goes as z minus z0 to the n plus 1. But again, that's more for a numerical analysis class, to worry about the error. And what we do in this class is we're going to truncate this series after n is equal to 1. So we're going to take the specific, special case of n is equal to 1. If the problem is one-dimensional, so if I only have, for example, x as a function of t, then I only need the interval. But sometimes I have my function f that's a function of 2 variables, say x and y, and if I write this part explicitly, if I write it in 2 dimensions, f of xy, so z is a vector xy, and that's equal to f of x0, y0, the center point, plus the partial with respect to x evaluated at the center times x minus x0, plus the partial with respect to y evaluated at the center times y minus y0, plus the next order terms if I were interested in them. And just for your edification, the next order term looks like this. It has a second derivative with respect to x, a second derivative with respect to y, and the mixed partial at the fxy. And all of these are always evaluated at z0. They're all evaluated at the center. So we truncate here. And with this basis, again, what we're doing algebraically is if we have a function, say, in this case, f of z, and let's say it looks like this, f of z, then what we're doing is we're approximating f of z. If this is z0, we're approximating f of z by the tangent. Let's just use another colored chalk there. And this is basically reviewed from last time. But we're approximating f of z by the tangent of the curve at z0. And as you can see, as long as I'm close to z0, that's pretty good. And again, I'm assuming that the function is differentiable here, that there's no break in slope or something. The function doesn't look like this, because here it wouldn't be differentiable. So assuming that it's differentiable at the point and near the point, then close to z0, this is a good approximation, but the further away I go, the worse the approximation is. So it's good to be close as opposed to far. Are there any questions on that idea before we do some examples? So let's do some examples. So let's let f of x be x to the 1/2, the square root of x. When I write it as the square root of x, which is x to the 1/2. Okay, so I want to write, first of all, is x to the 1/2 differentiable? Can I take the derivative of that? Yes, it's differentiable everywhere. So, so now I can write f of x, and let's say I want to do it about a certain point. Let's say about x is equal to 1. So I want to say this is, say, f of 1 plus something. So according to this, I need the derivative. This is only a function of one variable. I need the f dx at 1 times x minus 1. And then I have plus the quadratic term. So then plus the remainder, which we're not going to worry about. So f of 1 is, what's the square root of 1? Higher mathematics. Square root of 1? 1. And what's the derivative of the square root of x? So 1 over 2 square roots of x, evaluated at x is equal to 1, times x minus 1. What is the square root of x evaluated at x equal to 1? 1. So this is just equal to x minus 1. It's equal to 1 plus x minus 1 over 2. In general, if I worked about x is equal to 1, it would be f of x is equal to f of x0 plus 1 over 2 square roots of x0 times x minus x0 plus remainder. So that's sort of straightforward. Let's look at another example. Sine x. So I have f of x, sine of x, is equal to sine of x0, around some x0, plus the derivative of sine x. What's the derivative of sine x?
Cosine.
Cosine x here. And it's evaluated at x0 over 1 factorial. 1 factorial is just 1 times x minus x0. And just for fun, let's go one more term in. What's the second derivative? What's the derivative of cosine? Negative sine. So the next one would be minus sine of x0 over 2 factorial x minus x0 squared plus higher order terms. Now, let's look at a specific case. Let's say x0 is 0. For example, when x0 is 0, then I have sine of x is equal to the sine of 0, which is 0, plus the cosine of 0. What's the cosine of 0? 1. 1 over 1 factorial x times x minus 0. And then I have minus the sine of 0, which is 0. And if I go one more term, I get the cosine of x0 over 3 factorial x minus x0 cubed. And the cosine, again, is 1. So I've got 1 over 3 factorial x minus x0 cubed. X minus 0 cubed. plus R ordered terms. And you might recognize this series as, if I just rewrite it, only keeping the non-zero terms, it's x minus x cubed over 3 factorial, and if you keep going, it's x5 over 5 factorial, minus x to the 7th over 7 factorial, etc., which is the standard expansion for the sign of x about x equal to 0. Should what be minus?
The very last term.
Plus minus. This should.
Or after that.
Yeah, minus. Yes. Yes. It should be minus. And that's why I have. This should be a minus. Okay. But of course, I can expand about something else. It doesn't have to be about x equal to 0. If I have this expression, I can expand it about any x0. So for example, I could expand it about pi over 2. I also know that sine x is equal to the sine of pi over 2 plus the cosine of pi over 2 over 1 factorial x minus pi over 2 minus the sine of pi over 2 over 2 factorial x minus pi over 2 squared plus dot dot dot. And you can see the sine of pi. What's the sine of pi over 2? Higher mathematics? I can't hear you. What's the sine of pi over 2? 1. So in this case, I have sine of x is equal to 1. And what's the cosine of pi over 2? 0. And then I have minus sine of pi over 2, which is 1, over 2 factorial times x minus pi over 2 squared plus dot dot dot. So I can also do it like that. Okay, so far I have one example, 2 examples. Let's do another example. What's the one I picked out? X over 1 plus ax. Okay, so here we actually have to do a little bit of calculus. So f of x, and let's expand it about x is equal to 0. Well, let's do it first in general. So it's f of x0. F of x0 is x0 over 1 plus ax0. Plus, what's the, someone take the derivative of that. Somebody want to take the derivative of this? You can go through step by step. Do you want to take the derivative? You're looking at me and not reacting. This is basic calculus, it's a prerequisite for this class. Okay. Okay, so tell me. So the denominator squared is 1 plus ax0 squared. What's the derivative of the numerator? Wait. Okay, so derivative of the numerator is 1. So 1's the denominator. Minus the numerator, x. What's the derivative of the denominator? A. And x0. So this cancels. And I have x0 over 1 plus ax0 plus 1 over 1 plus ax0 squared x minus x0 plus higher order terms. So let's imagine if x0 was 0, then I have 0 plus 1 over 0 times x minus x0. So that's not a very interesting one. But then if I'm doing it about x0 is equal to 1, then I would get 1 over 1 plus a plus 1 over 1 plus a squared x minus 1. So this is if x0 is 0, if x0 is equal to 1, etc. Okay, so yeah.
For the top part, so it's 1 plus ax, and then you wrote minus xa. Shouldn't it be just...
Wait, first you have to tell me where on the blackboard.
So f of x...
Which line? Line 1, 2, 3, 4, 5, 6.
3.
Line 3, okay.
Yeah, so the second term, it says xa. Shouldn't it just be a?
Okay, so I've got the derivative of the numerator times the denominator. So that's 1 plus ax. Plus the numerator x times the derivative of the denominator. Plus the numerator x times the derivative of the denominator, which gives me the a. So that's why that cancels. Other questions? Okay, well, once we know that, now we can start doing a problem. Anything else I want to say before a problem? Okay, so let's look at the following problem. I have a CSTR. And I've got a reaction 2A goes to product, where Ra is minus 2K Ca squared. So I have the 2 here just for stoichiometry. You can lump it into the K if you like. I'd like to keep it separate. But since it's 2A, I have a Ca squared. And we're given that Ca in versus T goes through a step change at T is equal to 0. And what we want to find is Ca as a function of time. We want to find, and we know, and we're given that for T less than 0, the system is steady. So let's go through and do that. We write out the CSTR equation, dCA dt is equal to, actually, do I want Ca in to change or V in to change? Just so I have do the same problem. Yeah, Ca in. Okay. So we're also given that V doesn't change. V, which is the volumetric flow rate coming in, doesn't change. Unchanged. And therefore I have tau, which is the volume of the volumetric flow rate, is a fixed quantity. So here I have Ca in minus Ca over tau minus 2K Ca squared. So this is in minus out plus generation. Generation is negative because I'm using up A. So is this equation, you're comfortable with this equation? Okay, now we notice that this term has a Ca squared in it. Now Ca squared is nonlinear. So let's figure out what to do with that. Well, so here I have f Ca is Ca squared. So I have to use Taylor's theorem. So I have this is equal to Ca0 squared, Ca some sort of reference squared. And we'll figure out what that reference is in a second. Plus the derivative. What's the derivative of Ca squared? I can't hear a word you're saying. What's the derivative of Ca squared? I can't hear anything. 2Ca. If you're having trouble taking derivatives, it's very serious. If you're having trouble taking derivative of x squared, then I'm worried. So I've got 2Ca evaluated at Ca0 times Ca minus Ca0. Okay, so this is equal to Ca0 squared plus 2Ca0 times Ca minus Ca0. So I need to know what Ca0 should be. So this is the value of Ca for t less than 0. I'm sorry. This is Ca for t less than 0. So what I'm going to do is I'm going to let Ca0 be Ca for t less than 0. That's going to be my choice. So now I have dCA dt. So this is exact. And this is linearized. So I have dCA dt is equal to CA in minus CA over tau. And to be explicit, this is CA in for t greater than 0, minus CA. Minus 2k CA squared. So I've got 2k times a CA squared. Well, CA squared is CA 0 squared plus 2CA0 CA minus CA0. So where for CA squared I plug this in. Where CA0 I'm calling, actually why don't I write it out here? CA for t less than 0 squared plus 2CA for t less than 0 times CA minus CA for t less than 0. And now what I'm going to do, so I have the exact, and I have the linearized, and now this is all for t greater than 0. T greater than 0. And now what I want to do is I want to write out how things were initially for t less than 0. For t less than 0, I have a dCA for t less than 0 dt. Well, it was at steady state. So what was the derivative ddt of CA for t less than 0? About 0, because it was steady. Because we were given that it's steady state. And that was equal to CA in for t less than 0, minus CA for t less than 0 over tau. Tau hasn't changed. And now for t less than 0, I can write out the exact. It was minus 2k CA of t less than 0 squared. So all I did is I rewrote this equation for t less than 0. You with me? Now what I'm going to do is I'm going to take this equation and subtract this equation. And when I subtract, I want to define something. I'm going to define CA prime as CA of t greater than 0 minus CA of t less than 0. And I'll let CA in prime be equal to CA in at t less than 0 minus CA greater than 0 minus CA in at t less than 0. So the prime means greater than 0 minus less than 0. Okay, so if we subtract, I'll take this minus this. So this equation minus this, dCA minus dCA at t greater than 0 minus dCA at t less than 0. Well, that's just dCA prime dt. It happens this is 0, but even if it weren't 0, I would just have the derivative of CA minus CA at t less than 0, dCA prime dt. Now I have CA in at t greater than 0 minus CA in at t less than 0. What do we call that? What do we call something greater than 0 minus t less, the same thing at t less than 0? We just 30 seconds ago gave that a name. Prime. So that's equal to CA in prime over tau minus CA minus at t greater than 0 minus CA at t less than 0. What do we call that? CA prime. And now notice this term and this term are exactly the same. But since I'm subtracting this from this, they cancel. And all I'm left with are the other two terms. So I have minus 4k CA at t less than 0 times CA at t greater than 0 minus CA at t less than 0. What's CA of t greater than 0 minus CA of t less than 0? What do we call that? CA prime. So the difference between these two gives me CA prime. And the nice thing is that CA prime for t equals 0 is 0. By definition, CA prime at t is actually less than or equal to 0. CA prime at t equals 0 is CA at t equals 0 minus CA at t less than or equal to 0. So this is, by definition, 0. That's why we like the prime variables. They're called deviation variables. And the nice thing about them is the initial condition by definition is 0. So now notice we have a linear equation because we left out the other terms here. So this is approximate, but we're going to go with that approximate. And now let's notice, let's bring, as we did before, all the CA primes, that's my variable, let's bring them to the left. So I have dCA prime t plus CA prime times 1 over tau, that's this term, plus 4k CA at t less than 0. And that's equal to CA in prime over tau. It's exactly the form that we had here, where x is CA, where x is CA, and where A of t and B of t, here's A of t, here's B of t, are both constants. Because this is CA in prime at t greater than 0. And this thing is 1 over the time constant. 1 over t. And notice the time constant here, 1 over t, is 1 over tau plus something. So if 1 over t is bigger than 1 over tau, because I'm adding something to it, that says that t is smaller than tau, because 1 over t is bigger than 1 over tau. So that says when I have a reaction, the characteristic time t is shorter than if I don't have a reaction. Duh. I'm not only getting rid of A by virtue of flow, I'm also getting rid of A by virtue of reaction. So it should be faster. And it is. And now we can immediately write out I have CA prime of t. Because they're both constants, I can appeal to this equation. And the initial condition is 0, because CA prime of t of 0 is 0. So this term is 0, so all I have is B over A. B over A is CA in prime. The difference, CA in prime, this is CA in prime. CA in prime over tau, that's B over A, t, times 1 minus e to the minus t over b. And this is the linearized problem, solution to the linearized problem. And let's plot that for a second. So here is CA, here is T. And this was, here's 0, and it was steady beforehand. So this is CA of T less than 0. And now let's see what happens. Well, I have something that rises like an exponential upside down. So it rises like this. And this is the linearized solution. And let's notice that it has a time constant t. And now I'm kind of curious to know, by virtue of the linearization, am I overestimating the concentration or underestimating the concentration? So let's notice for a second that what we did in the linearization, which we did somewhere we did here, we took a function f of x versus x. So this was f of CA. versus CA. And this is CA squared. CA squared looks like this. That's the true function. When we linearized it about a certain value, So let's say this value is CA0. So you notice that when we linearize it, because the function is convex, because it has that convex curvature, then we've underestimated C. If we underestimated C, we underestimated the rate of reaction. So if we underestimated the rate of reaction, the real reaction ate up more CA. So it says that the real solution is going to have less CA. So it's going to be pretty good close by, but eventually it's going to miss the real solution. Now, I don't know exactly what that is, but I know it's a little bit lower. Yep.
I'm confused about us using this CA prime. Why can't we just solve the second equation?
The second equation. This equation?
Yeah.
You can.
Oh, okay. So we're
This is just easier because it gets rid of some of the terms. And the nice thing, the reason we use the deviation variables is because it gives me initial condition 0. So I automatically have this term being 0 or this term being 0. So it's less writing. And the less you write, the less likely you are to make a mistake. But yes, you can just solve the second equation. This is just a little easier. Yep.
So like when we're estimating whether or not the linearization is over or underestimated, if you have a real function that kind of lives above and below the linearization, how would you
Again, it depends on the specific function. The question is what happens close to the point about which you linearize. Obviously, the approximation, linear approximation, is only good close to the function. The error goes as z minus 0 to the n plus 1. It goes z minus 0 squared. The further away you get, the worse it is. So if it dips below the linearization far away, then it's not very good far away anyway. But you have to look exactly where you're doing the linearization. And then, so for example, let's say you're linearizing about an inflection point. So on one side it's above, on the other side it's below. Then to see if you're overestimating or underestimating, you have to see, are you on the right side or on the left side? Are you above it or below it? And then you'll know if you're overestimating or underestimating. But here, it's straightforward because this is a convex function. It has that convex curvature, an increasing first derivative.
You chose the x0 point as less than 0.
I chose the t equals 0 point as the reference point. So I chose this. That was a choice. I could linearize. I chose it because I know the concentration was there at some point. And it's only, the approximation is only good close to that point. So I had better make sure at least sometimes I'm close to that point. So I chose it because I know that t equals 0 was there. So that's why I chose it that way.
Would there be another time where you choose a different point, let's say the midpoint of the range?
It all depends on the situation. But if you know that you're going to be close to there, then yes. Other questions? While we're at it, why don't we calculate steady state gain? This is called steady state gain. And remember we said that's the delta out over delta out as t goes to infinity over delta in. So delta out is the prime. So that's CA prime as t goes to infinity over CA in prime. So CA prime as t goes to infinity CA prime as t goes to infinity. What happens to the exponential as t goes to infinity? It goes to 0. So I just have this guy over this guy is t over t. T over tau. And since we know what t is, so this is t over tau. T is the inverse of this. 1 over 1 over tau plus 4k CA t less than 0. And this is divided by tau. So this is 1 over 1 plus 4k CA t less than 0 tau. And in fact, this is something you generally would calculate in your kinetics class, because remember, your undergraduate reaction engineering class is still in steady state land. We're in the real world, but we also calculate steady state, but not only. Your reaction engineering class only calculates steady state, and you would find this value. Are there any other questions? Any questions on this? No? Delta out or delta in? OUT. Other questions? Yeah? Can you speak slower and louder? How about what? C product? Oh, well, you can do that too. In this case, it's just stoichiometry. Well, not only, but you would start, if I'm interested in the product, let's say this goes to B. Let's say the product is B. So I would have dCB dt is equal to CB in minus CB over tau plus, in this case, it would be KCA squared. Because stoichiometry tells me I use up 2 A's when I make 1 B. So I have plus KCA squared. Now, of course, you need to know what CB in is. I haven't told you that. That would be. And then from the stoichiometry, you would try to relate CA, the reaction of CA to the reaction of CB. I'm sorry, from the stoichiometry, you would try to relate the amount of CA to the amount of CB. So I would need that. I would have to relate CA to CB in order to actually solve this equation, because I can only have one dependent variable, CB. Or I would just try to solve them both together. So, for example, here I have CA explicitly as a function of time. So then what I could do is I could plug in for CA. This is just CA of t now. This is known. It's a known function of t. Here, I just solve for it. So now I can solve it. I can now take dCB dt plus CB over tau is equal to CB in over tau plus KCA squared of t, which is known. Because I just solved for it. It's known. Here it is. So now A is just 1 over tau, and B from this equation here, B of t is now a function of t is equal to this. So here I have B of t, here I have A, and now I just plug into this formula right here to get B of t. So that's the most straightforward way of doing it. Now, if there's no B in the feed, then CB in is just 0, and then I just have this. But that's a very, very good question, because it's really the next step of what you would do once we have CN. Other questions? I like these questions. Keep them coming. Other questions? How did I get 4? Okay, well, I linearized this. So CA squared is CA0 squared plus 2 CA0 CA minus C0. But I have 2 in the rate function. So 2 times 2 gave me 4. Now this is totally my choice. I could have lumped the 2 into the k. But if I did that, then I would have had to have a 1/2 here. So generally, what we frequently do is we include the stoichiometric coefficient in the rate function explicitly. So we have a 2 here, and it's on the left side of the arrow, so it's a -2 because it's being used up. And on the right side, I have 1 on the right on the head side of the arrow, so it's a +1. So that's why I have a +1 here, and I have a -2 here. -2 because I'm on the tail of the reaction arrow, and the stoichiometric coefficient is 2, and +1 because I'm on the head of the reaction arrow, and a stoichiometric coefficient 1. Other questions? You don't have to do that, but the ratio has to be the same. So I could have lumped the 2 in here, then I would have needed a half over here if I want to use the same k, and that's harder. It's just easier to use the stoichiometric coefficients. Yeah. Which you do here, because you have a non-zero concentration because beforehand you were in steady state, so you had some V. But you can continue the question, or did I answer it already? And you were saying if, but yes, that's exactly the case we're in. And of course, over here, so remember CV at t equals 0 is the steady state value, which you get, which we know, which we calculate from here. So it's not 0. Other questions? Okay, why don't we do another little example? No one calls all day, only when I'm teaching. Okay, so let's do another example. Let's say I have a tank, and I have fluid coming in, and I have fluid going out, at a certain level of L. L. And I've got a V in, volumetric flow rate in, and a volumetric flow rate out. And there's a cross-sectional area. This is the cross-sectional area A of the tank. So, and let's say we're given that for t less than 0, V in the system's in steady state. And V in undergoes a step change at t is equal to 0. And we want to find L of t. And we're also given that V out is equal to some k times the square root of L. And in 2 classes ago, or 3 classes ago, I showed you where this comes from. This comes from just Bernoulli's equation. That is square root of L. And the assumption is the whole here is L is the height of 0, where L is the difference between these heights. Okay, so we know that dL dt times the cross-sectional area, because L times the cross-sectional area is the volume. This is word 3. And that's equal to V in minus V out. And V out is equal to K square root of L. So that's exact and it's nonlinear. Notice how I'm doing this. I have exact, linearized, less initial condition. So this is exact t greater than 0. Now I'm going to do linearized t greater than 0. So I've got L, A to L T is approximately equal to V in. And now V out is square root. Well, we already did the square root. So I should get the value I started with. K times the square root of L0 plus 1 over 2 square roots of L0 L minus L0 plus higher order terms. And this is linearized for t greater than 2. When you do problems, follow these steps. Exact, linearize both t greater than 0. And now I want initial condition. Exact. So the exact is a the L at t less than or equal to 0 dt, which happens to be 0 here because it's steady, because I'm given steady. But it didn't have to be. And that's equal to V in minus K square root of L t less than 0. And that this is L at t less than 0. So now I'm going to subtract the third line from the second line, just as I did over here. I subtract the third line from the second line. So if I have A times, what is L minus L0? What are we going to call that? L prime. And that's going to be V in, this is t less than 0. What are we going to call V in at t greater than 0 minus V in at t less than 0? V in prime. Now notice this and this are the same, so they cancel. So what I'm left with is minus K over 2 root L0, L minus L t less than 0, that's L prime. And now I devote both sides by A. And I have an equation, again, that's a first order linear differential equation. That's not an accident. I made it linear by linearizing. It wasn't a miracle. That's exactly what we wanted to do. So now we bring this to the other side of the equation, the L prime dt plus K over 2A root L0, which we now call 1 over t. L prime is equal to V in prime over A. And again, this is A, this is B, in my formula up there. And I know that L prime of T equals 0 is equal to 0 by definition. And again, that's why I like the prime variables. So it tells me that the first term I can forget about. And that tells me that L prime of T is equal to B over A, so V in prime over A, divided by A, K 2A root L0, these cancel, as they should, times 1 minus e to the minus t over 2. And now if I plot it, I have L of t, prime of t, versus t. So I have a certain value, and if it went up, then it looks something like this. That's if V prime went up. If V prime went down, then it would, then if V prime were negative, then it would go down. Here I assume V prime is positive. And now let's just see, are we overestimating or underestimating? So in this case, we're approximating the square root is a concave function, not a convex function. So the tangent overestimates. Tangent overestimates L. So the tangent, because the tangent is higher than the function, this is concave. Since it overestimates L, it overestimates what's flowing out. It overestimates what's flowing out. So what's in there is more. So the true solution, we know, is going to be a little higher. It's going to be good in the beginning, but eventually it's going to miss. So that's the non-linear. A little higher. Questions? Again, let's just look at KP, the steady state gain. That's L prime of infinity over V in prime. So it's this at infinity over this, and infinity this, I left the minus, and infinity this drops out. So I just get 2 root L by t less than 0 over k. It's a steady state gain. Any questions? We'll do one more example. In the meantime, someone might want to take a picture of the first 2 blackboards because I think I'm going to be erasing. So this is a CSPR heater cooler, with no reaction. So what comes in is I have fluid coming in with a V in and a theta. Remember, I'm using theta for temperature because I've claimed big T for time constant. And then, of course, I have a theta and a T here. A theta and a V, well, just a theta here, and a theta here. And for the coolant, I have a theta coolant in, and I have a V for the coolant. Actually, just call it V coolant. Let's call it V. And of course, I have a theta C out. So what happens here? What happens here is I have fluid coming in at a certain temperature. It's being mixed and it's being cooled down. Let's say hot fluid, and it's being cooled down by contact with a coil that has cold fluid going through it, and then it comes out at a colder temperature. So we would like to look at this problem. And I'm going to assume that the kinetic energy, potential energy, and the shaft work all 0, all negative. So I have du dt is equal to h in minus h out plus q. So I've got flow. I'm changing the energy by having, let's see, is there anything else I want to say here? Yeah, that's fine. So the internal energy changes by virtue of heat flowing in, enthalpy flowing in, enthalpy flowing out, plus the amount of heat transferred from here to here. And actually, the heat transfers from here to here, so I'm going to call it minus, because it's going from the reactor to, well, it could be a heater or a cooler. I'll just, to be consistent with my notes, I'll keep it plus. I have a plus in my notes? I'd just like to be consistent. Yeah, okay, there's a plus. So if you like, this could be either heating fluid or cooling fluid. I just call it C. All right, so U, we know, is rho times V Cp times d theta dt, where Cp refers to the fluid in the reactor. And this is rho volumetric flow rate times Cv times H in would be theta in minus theta reference minus rho v CV theta out, which I just call theta, minus theta reference, plus Q. So the first thing I can do is I can get rid of theta reference because it's the same in both terms and they're with a negative sign, so they cancel. So this is the balance on reactor fluid, or CSTR fluid, not reactor. And I'm also going to assume that CP is CP, so I don't have to worry about the difference there. Okay, now the one thing I need to know Q. I don't know Q yet. So in order to get Q, I need to do a balance on the coolant fluid. So let's do a balance on coolant fluid. And I'm going to assume that the coolant fluid reaches steady state much quicker. Why? Well, it's a small tube, and I'm going to assume that the heat transfer is big enough in that tube that it reaches a steady state more quickly. Notice that in the big reactor, because it's stirred, the temperature's the same everywhere. Whereas in the coolant tube, the temperature changes as I move along the tube. So I'm going to assume steady state. So I have a 0 here. And here I have a rho of the coolant, the volumetric flow rate of the coolant, the CV of the coolant, little c is that. And it's going to be theta coolant in minus theta coolant out. So it's the analog of these two. And if this was a plus going into the fluid, then it's a minus coming out of the coolant. So there I have an expression for Q. So in theory, I can take this expression for Q, which is this, and plug it in here. The problem is, this is theta, d theta dt. And I know the coolant temperature coming in, and I know theta coming in, but I don't know theta coolant coming out. So I don't want to have anything in the equation that depends on what comes out. So I need another equation to relate what comes out to get theta C out in terms of theta C in. It's a clear why I need that. Because I don't want anything, I don't know theta C out. I want to predict what's coming out. I don't want to need what's coming out in order to get what's coming out. Okay, so you know from your unit ops class that Q is UA delta T log mu, where U is the overall heat transfer coefficient, A is the area of the tube, and delta T log mean is a log mean temperature difference. It's a delta T over delta log T. Now that's very nonlinear. So that's too hard. That's nonlinear. So we're going to come up with a simple approximation. And so let's zoom in on the tube. So here I'm not worrying so much about its shape. I could, I could start drawing it with all sorts of shape, but in any case. So this is the coolant tube. And what I'm going to do is I'm going to let this variable be Z. So here's Z. Going through the coolant tube. And what I know is, let's think about Q, what Q is there. I can write Q is equal to U times, well, the area. So I've got to let's say this has a radius A, so it's 2 pi A times, so on a little piece of area, it's 2 pi A dz. On a little area, say from here to here, this little piece of area. So this is, that piece of area is 2 pi A dz. The heat transfer is the heat transfer coefficient times that area times theta. So I'm defining it as plus if it's going into here. So it's theta of the coolant minus theta of the fluid. Where this is a function of z, but this is not a function of z. So dq in this little piece is u times 2 pi a is the radius, times the local concentration gradient across here. So I've got a theta c of z, and I've got a theta out here, but since this is well mixed, this theta is the same everywhere. And now if I want all of q, I have to integrate that over all z. This is dz, not ds. We say 0 to L, where L is the length of the coolant tube. Is that clear? Is that clear what I'm doing? Now, I could do a whole derivation to do this properly and get delta T log mean. But we're going to do a baby derivation, which is kind of silly, but I'm going to divide, multiply, well, so this is what I have. Now what I'm going to do is I'm going to multiply and divide by L. So if I multiply by L and divide by L, what happens? This is the total area. That's the total area. And what do I have here? I add up, what I'm doing by integrating is I'm adding up the difference and dividing by what the region I'm adding over. So it's like I'm adding up the grades in the class and dividing by the number of students in the class. What do I get when I do that? I get the average. So what I'm getting here is the average of theta c minus theta. Now, we know that the average is going to be delta theta log mean, delta theta log mean. But I'm going to take a dumb average, and I'm going to write this as UA times 1/2 the value at the beginning, it's the value at the end. 1/2 of theta c minus theta at c equals 0 plus theta c minus theta at c is equal to n, where this is in and this is n. Now, is that right? No, it should be delta theta log mean. But this is an approximation. I'm going to say, instead of taking the real average, I'm going to take the highest grade and the lowest grade and average them and assume that the average of the highest and the lowest grade is representative of the average in the class. Is that really good? No, but it's linear. That's what we're stuck with here. Okay, so what is it? So let's just rewrite that. That's just saying that we can write Q as approximately equal to UA over 2 times theta C in minus theta C out let's leave the 2 in here. Plus theta C in plus theta C out minus theta. So I brought the half back in. I had 2 theta over 2 just gives me theta. And this is what I have. So let's notice I have one equation here. an equation here, and an equation here. And let's try to follow the logic. I have this equation for the fluid, and I need an expression for Q. I come up with an expression for Q, but then I introduce something else I don't know, theta C out. So I need another expression for theta C out. Here's another expression that relates theta C out to Q. So now between this expression and this expression, I can eliminate theta C out and plug in for Q here. Now there's one other thing, is that UA, the overall heat transfer coefficient, in practice depends on the volumetric flow rate, because it depends on how much turbulence there is in this in the tube. So what you find empirically is that UA can be written often as A V coolant to the B, where B is less than 1. And A and B are given constants. So now we're ready to actually combine things and do something. We have a picture of this board, right? Yes. Okay, so here's board 4. So the first thing is I'm going to take equations, let me number these. So here's equation 1, equation 2, equation 3, and equation 4. So let's take 2 and 3. Let's combine 2 and 3. Okay, so let's notice in, I want to eliminate theta out. Okay, so, yeah, so let's write, I have Q is equal to, Q equals to rho CVC CPC times theta C in minus theta C out. So I'm just rewriting theta C in minus theta C out. And equation 3, so I don't have to keep running over here, is Q is UA times the average minus theta. Theta C in minus theta plus theta C out over 2 minus theta. Okay, so now I'm going to plug in theta C out from this equation. So this is equal to UA times theta C in, so 1/2 of theta C in plus theta C out. Well, theta C out, I know from here. From here I can solve for theta C out. And that's equal to Q. Now notice I have a Q on both sides of the equation. So I have to bring this over to that side of the equation. And let's bring the half in, so it's not just sitting on the outside. Okay, so now I have theta, I'm sorry, this is a Q. Q times 1 plus UA over 2 rho CVC CPC. So that's this term plus this term is equal to UA times theta C, 2 theta C ins over 2, it's just theta C in minus theta. And there was no half here. So I've got UA, so I move this to the other side of the equation, and this is what I have left. So this tells me that Q is equal to UA theta C in minus theta over 1 1 plus UA, 2 rho C VC, CPC. So I just solved these two equations to get an expression for Q in terms of theta C in, only in terms of in things, because I got rid of theta C out. And now I can plug in for UA. We know that this is A, B, C to B. Theta C in minus theta. Over 1 plus A, B, C to B. Over 2 rho C, B, C, C, B. Okay, so this is Q. And now I can finally plug in to this equation. So here I've used equation 4. And now I go to plug into equation 1, which is the balance in the whole world reactor, which I can do up here, which is rho VCP, d theta dt. This is the equation I want. And this is equal to rho VCB, which I'm going to drop CB and CP because I've assumed that they're both the same. I'm just going to call them C. Rho VC. Let's call them both CP so we're not confused with coolant. CP times theta in minus theta. And now instead of Q, I have this thing. So I have A, VC to the B, theta C in minus theta, divided by 1 plus A, VC to B, over 2 rho C, VC, C and C. And let's look at what we have here. First, we've gotten rid of all the variables we don't like. We didn't like Q because we didn't know Q. We replaced Q with this expression that gave us a theta C out, which we also don't know. So then we use this equation to get rid of theta C out in terms of Q, and then we can plug in for Q and get this. Okay, so let's notice this is a derivative, this is a linear term, a constant and a linear output. And this now, the last term, is some function of VC, which we say changes. Actually, I probably didn't even mention that. We're given that VC of t looks like this, and here it was steady state. So VC changes. So this is a function of VC, but it's also a function of theta C in. It's also a function of the inlet coolant. But we're going to assume that theta C in doesn't change, but it also is a function of theta. So VC changes, and that causes theta to change. So this is both theta and VC in it. So therefore, and it's nonlinear because I'm multiplying VC to a power, and it's being multiplied by theta. And I also have VC to the power in the denominator. So that's nonlinear, and it's a function of two variables. So I have to go to this expression right here to figure out exactly what it is. In other words, I have f of VC theta is equal to f of VC theta for t less than 0 plus df d theta for t less than 0 times theta prime plus df dvc for t less than 0 vc prime, which is exactly what I wrote down here. Well, we have a limited amount of time today, but let's notice that this thing, f of vc theta for t less than 0, is equal to a vc t less than 0 to the b, theta c in minus theta t less than 0, over 1 plus a vc t less less than 0 to the b over 2 rho c vc t less than 0. Well, actually, since I have a vc down here, I'm going to multiply top and bottom by vc to get rid of this guy. If I multiply top and bottom by vc, I have a b plus 1. And that got rid of the vc in the denominator. So this is to the b, this is to the b plus 1. This is vc t less than 0. And this is 2 rho c cbc. And let's just do the derivatives before we are gone. The f d theta, t less than 0. Well, d theta, I have a theta here. This term has no thetas in it. It only has a theta c in it. So this term, when I take the derivative, is independent of theta. So that's 0. But this term is not independent of theta. It just has a theta. So I just get minus a vc t less than 0 with b plus 1 over vc t less than 0 plus a vc t less than 0 b over 2 rho c cbc. So we have the f d theta for t less than 0. And the only thing left I need is, so what I've got this, and now I need the f dvc for t less than 0. Okay, so one thing that's going to come out is the a and the vc, a theta c in minus theta. So if I take that out, now I have the numerator and the denominator both depend on vc. So I take the derivative of the numerator, which is v plus 1 vc to the b, times the denominator, vc plus a vc to the b over 2 rho c cbc. F prime g minus f g prime minus v c to the b plus 1 times the derivative of the denominator. Well, the derivative of this with respect to c is 1. And the derivative of this is ab vc to the b minus 1 over 2 rho c cbc. And this is all evaluated for t less than 0. So now I have all these guys. I know exactly what the FDVC is, it's this. I know what the FD theta is, it's this. And I know what F is. And the important thing is, F, and both of these derivatives are evaluated for t less than 0. So that says that now I'm replacing this term by this plus this times theta prime plus this times vc prime. I've linearized the problem. And I can rewrite the equation, which I think is about where I'm going to run out of time, is I'm going to divide through by this. So I have the theta dt. This term is going to move to the other side of the equation. So I've got plus theta times, well, when I divide by this, I have little v over big V, which is 1 over 10. And what else do I have? And now I also have, remember, I want to get all the theta stuff to the other side of the equation. So I have this term, so I've got minus the f d theta, the f d theta at t less than 0, theta prime. So I get all the theta stuff on the left. And what's left on the right? What's left on the right is f of vc theta t less than 0 plus df dvc t less than 0 vc prime. And I have the inlet, which is theta in divided by 10. So here's where we're going to have to end today. I won't get to finish the problem. But let's just bring you back to the general way we were doing these problems. There was more algebra here because we needed more equations. But remember, the way we do these problems is we write out the exact equation. This is the exact equation for t greater than 0. This equation now is the linearized equation for t greater than 0. Remember the steps. Exact t greater than 0, linearized t greater than 0. The next step is exact t equals to 0. The exact t equals to 0. And then we're going to subtract the exact t equal to 0 from the linearized t greater than 0. And that's going to give us a linear first order differential equation to solve. So we'll finish that in the beginning of the next class. But let me just, again, review what we did in this last example because it's more complicated than the previous examples. So what we did, again, we started out by talking about linearization and how to do linearization. And then we did 3 examples where we write out the exact balance, which is nonlinear. We linearize it, and then we subtract the exact equation for t less than 0. Here, we wrote out the exact equation. It just had variables we didn't like, so we needed 2 or 3 other equations to eliminate q to get it in terms of theta in VC. That's the last 20 minutes of algebra. We're turning q into f, where f only involves VC and theta. Once we did that, this is the exact equation. This is the linearized equation, which we just did. And the next step, of course, is to take the exact equation for t equals 0 and subtract it from here, get a linear equation, and use those equations to solve. Are there any questions? Okay. Any questions? All right, so I will give you a homework on this. Once we finish this problem, which is not very far, there'll be about a little short discussion of numerical solutions, and that will complete the material for the first exam. So make sure that you're up to date on doing the homeworks and asking questions. I'm going to continue. I'm going to start the material for the next exam already in the middle of the next class. But the material for the first exam is going to end once I finish talking about numerical methods. So you really don't want to fall behind. You want to make sure that you're keeping up to date. And the exam will probably be, I'll have to look at the calendar, probably a week from Wednesday, is my guess. But that may still change depending on, what you need to do is you need to hand in your homeworks and get your homeworks back before we have the exam. So it's possible that it could change either a week from Wednesday or the following Monday. Questions? Okay, as a recall, I have office hours on Thursdays from 4 to 5. And you have the TA, so feel free to come and ask questions. Is Professor Steiner using this room?